Greetings everyone. Here we are again with another FreeCAD tutorial video. Today, I'm going to show you a solution to a problem I proposed not long ago, one that was part of the competition organized by Too Tall Tovy. This particular challenge was presented during the finals on October 4, 2024. Before we dive into solving the problem, I invite you to keep an eye on the top right corner of the screen, as useful links to other videos will appear there. Now let's highlight some important details about this project. The goal in the competition is to design this picnic table, which consists of several parts, and then report its total mass. This mass depends on the densities provided for each individual piece. It's important to note the presence of two symmetry planes that divide the table into four identical parts. Our strategy will be to model just one of those parts and then use mirroring operations to complete the entire structure. The workflow we'll follow has already been explained in a previous video. The image you're currently seeing, showing the views of the table, will be imported 3 times and arranged accordingly, as previously explained. According to the workflow we're using, all the data defining the structure and shape of this table will be stored in master sketches, and possibly in some secondary sketches. From there, the rest of the project can be completed using the part design workbench, employing tools such as Subshape Binder, Additive Sweep, Subtractive Sweep, and Multi-Transform. Alright, let's get started with the actual modeling. Once the images are imported and properly arranged, we'll check how it looks. Is this okay like this? Next, we'll move to the Sketcher workbench to create the necessary master and secondary sketches. Depending on the complexity of each part, I'll first explain how to model the tabletop, then the benches, and finally the tubular frame. To create the tabletop, we'll start by designing its profile and its corresponding path, based on its thickness, to perform an additive sweep. Then, we'll apply a subtractive sweep to create the groove. Once this is done, we'll apply 2 mirror operations. The first gives us half of the table, and applying a second mirror to that result gives us the full tabletop. For the benches, the process is similar. We create the cross-section, sweep it according to its thickness, and then mirror it twice to obtain one bench. Then we mirror that bench once more to get the second one. For the tubular frame, we'll proceed as follows. We'll model only one of the 4 symmetrical parts, sweep its section along its path, whose trajectory we can see, and once we have the additive sweep of the structure, we'll apply the same mirror operations used for the table to complete the frame. Let's now describe the sketches we'll use in this project. We'll use 2 master sketches, one on the XY plane and another on the XZ plane. These 2 sketches will contain all the numerical information for our project. First, let's look at the XY master sketch. In this sketch, we define the horizontal dimensions of the components, for example, the cross-sections of the tabletop and benches, as well as the horizontal dimensions of the tube. Now, let's move to the XZ master sketch. Here we place the vertical dimensions such as the height of the structure and the thicknesses of the table and bench. Does that make sense? Next, let's look at the sketches that define the tube, a cross-section and a path. Since the path isn't flat, we'll need 2 separate sketches. The first segment lies on one vertical plane, and the second segment is on another vertical plane. We also place the cross-section in one of these sketches. What we'll do next is perform an additive sweep of the section along the defined path. Notice how the master sketches are used to define the secondary ones. Now, let's examine the sketches that define the benches and the table. Pay attention to how the profiles and sweeping paths are defined. We'll sweep the bench profile and then the table profile along their respective paths. You can clearly see the dependency between the secondary sketches and the master sketches. All dimensions in the secondary sketches are defined within the master sketches. Now, we switch to the part design workbench to create the solid bodies. We'll start with the tube. we'll create two subshape binders, one for the profile and another for the path. Then we'll perform an additive sweep using both elements, completing this step for now. Next, we apply a multi-transform operation, a mirror across one plane, and then another mirror across the second symmetry plane, resulting in the complete tubular structure. We follow a similar approach for the benches. We create a subshape binder for the profile and for the path, then perform an additive sweep to generate one bench component. The bench includes a groove where the tube fits, which we achieve using a subtractive sweep. For this subtractive sweep, we create a subshape binder using the external cross-section of the tube, and the path corresponds to the first part of its trajectory. Performing the subtractive sweep results in the groove you see here. After that, we apply two mirrors to obtain one complete bench, and then another mirror to complete the second bench. For the table, we follow a similar process. We create a subshape binder for the profile and another for the path, and perform an additive sweep. Remember, the table also has two grooves to fit over the tube, achieved using a subtractive sweep. For this, we use a subshape binder from the outer end of the tube to get the profile, and the path is obtained via a subshape binder from the final segment of the tube's path. Performing the subtractive sweep creates the groove for the tube. Finally, we apply two reflections based on the appropriate symmetry planes. That completes the table. With the design finished, we now need to report the total mass of the table. For this, I've added three properties: density, volume, and mass to each of the three main bodies: the table, the benches, and the tube. The volume is calculated using the expression shape volume, and the densities are those provided in the problem. The mass is then calculated by multiplying the density by the volume for each body. However, FreeCAD fails to correctly calculate the volume of the tube. I've reported this issue, and I hope the developers fix it soon. To work around this, we can consider the tube as the result of subtracting the inner solid bar from the outer solid bar. Since FreeCAD calculates volumes correctly for solid bars, taking the difference between these volumes gives us the accurate volume of the tube. Multiplying by the density then gives us the correct mass. In the competition, the winner reported a mass of 157.3 kilograms. Within the accepted tolerance of 0.3 kilograms, our calculated mass of 157.4 kilograms closely matches the official result. Before I wrap up, I invite anyone who watched the video to ask any questions if something wasn't fully explained. Please feel free to reach out, I'd be happy to clarify or add more information. And that's all for today. If you enjoyed this video, as always, I encourage you to subscribe to the channel, hit the like button, enable notifications by clicking the bell icon, share the video, and leave your comments, they're always welcome. Thank you for watching. See you in the next video. Bye for now.